this video, I want to tackle the topic of undamped forced vibration. So recall that previously we've been discussing free vibration. And in free vibration, for example, one version of it has a mass hanging from a spring which is attached to a fixed support, and the mass gets represented as a weight, a force applied to that rigid body, and that force is a constant. So then our analysis of this provided a differential equation of this form, where we have mass times acceleration plus the spring constant times displacement x equals to 0. And we replaced, or rearranged rather, this equation to get something like this. And we eventually substituted in natural frequency in place of k over m. So in forced vibration, we're no longer going to say that this load applied to the mass is a constant. So instead, let's say we have a fixed support attached to a spring, which is attached to a mass, and a force is applied to this mass. But now this force is not a constant. It is instead applied in a sinusoidal way, with a sinusoidal function. So according to this equation, we have some amplitude of our force, and then we have the frequency with which it's applied. So this is the frequency of our force that is applied to our mass. And if we plotted that, versus time, we would get some sinusoidal function which has a given amplitude and a period associated with it, which is the same as what we saw before in relation to the frequency, in this case, not natural frequency. So if we take this mass and pull it out and look at it as a free body diagram, we would have the weight applied to it and some normal force. And we have our varying force F, and then we have some spring force in the other direction. So we can use this free body diagram in order to write some equations. So for now, I'm only going to worry about the x direction and say that the summation of forces in the x direction is equal to mass times acceleration, and that's going to give us then F, which is F naught sine omega naught t. In the other direction, we have the spring constant times displacement, so that's our spring force. And then we have mass, and we have acceleration, which I'm going to rewrite as x double dot as we did before. So if we rearrange this equation, we can get it in a form similar to what we saw before, with x double dot plus k over m x, and then our non-x terms, and we get something that looks like this. So because this equation is not equal to 0, meaning there's non-zero terms that don't involve x, we would consider this a non-homogeneous second-order differential equation. So if we were to solve for x, from this equation, we would get something of the form, and again, I'm not going to go through the derivation of the solution because we're not well versed at this point in differential equations, but I'm going to get a solution of a form that looks like this. And this solution contains kind of two main parts. This first part over here is called the complementary solution, and this is due to the free vibration. And because it's a result of the free vibration, we're going to say, or assume maybe rather, that it's going to dampen out. Because of friction and other losses, any free vibration portion of our solution is going to eventually dampen out. So because of that, we call it transient, with regards to the notion that it doesn't stick around. It fades out with time. The right-hand side, the right-hand term, is our what's called the particular solution, and it is a result of the forced vibration. And the forced vibration stays around because there's some input driving it. So as a result, we refer to this as the steady state solution, and therefore we don't expect it to dampen with time. And that's important from the perspective of how we actually look at what's going to result from this forced input to the system. So if we look at this steady state portion, once again we have something very similar to what we saw for the input to the system, in that we have an amplitude and we have the sinusoidal portion. So the amplitude of this expression is out front here. So if I pull that out and isolate it by itself, this is my amplitude of my resulting motion that I'm going to get out of this. So it's the amplitude of my steady state vibration. And the one thing that we should note here, or make note of, is that omega n, so the natural frequency, appears in this equation. So this resulting amplitude is dependent on this ratio omega naught over omega n. And that's particularly important. So what we're going to do with that then is define something that we're going to call a magnification factor. Taking the denominator of this expression and kind of separating it out. So if we define this magnification factor, the name magnification factor kind of gives away what it's going to do. But if we were to plot this, we would get a plot that looks something like this. And what we should note, and what I'm plotting here, which I didn't show, but what I'm plotting here is omega naught over omega n and magnification factor on the y-axis. So if we look at this, what I should see right away is that as omega naught over omega n approaches 1, which is basically where omega naught equals omega n, the magnification factor goes very large. So it goes asymptotic and basically is unstable. And so what we get or should learn from that is when omega naught is approximately equal to omega n, the amplitude goes very big. So that amplitude is the amplitude of our output motion, our x. That's what we were solving for up here, is the position x of our mass. So when this occurs, we're getting a very large output for our input that we're putting into this. And this condition, where the vibration is equal to the natural frequency, or the input vibration is equal to the natural frequency, is called resonance. And we've probably seen this before in that when we apply a force or a load to something near its resonant frequency, we get very unstable reactions. So things tend to move more than we would expect them to, and it's just not a good situation. So in the design of machinery, in the design of any sort of vibrating components, this large amplitude output is not a good situation. It's likely to lead to failure because the stresses and the resulting forces being applied to our part are much, much larger than they should be. So that can be a problem. Now, we've expressed all of this in terms of a varying force being applied to our mass. However, we could just as easily have run the same sort of simulation or problems set up using, for example, a mass attached to a spring, attached to, let's call it a plate or something like that, in which the motion or the displacement of this plate follows some sinusoidal input. So rather than applying a force directly to my mass, maybe I'm moving the fixture that it's attached to back and forth. In which case, we could write the equation, in the same way. We could take our sum of forces in the x direction equals mass times acceleration, and we'd end up with an equation that looks like this. Where basically the only thing that's changed is that instead of F naught, we have this K delta naught in here. And that's really because our free body diagram has, weight again, resulting normal force, neither of which we really care about at the moment. There's no force being applied. So now our spring force is equal to Kx minus this sinusoidal input. So this spring force is varying, and then we get a very similar looking differential equation as a result. So it changes a little bit about the equation, but the net result is the same in that as the input frequency, omega naught, which is our driving force or our driving input, approaches our natural frequency, we get very unstable conditions. And that's problematic from an engineering design perspective. All right, so I'll stop there. Thanks.